We're going to go a little bit beyond the scope of the CCNA security exam, and you may think, well, this scope is so broad, I don't know how that's possible. But it is, but I want you to get an idea of exactly how Diffie-Hellman does what it does, because you hear all the time, and you've heard it from me a couple of times here in this course, well, it's a secure key exchange over a non-secure channel. And if you're like me, your first thought is, well, how the heck does that happen? You know, you've got a non-secure channel. They call it that for a reason. It's non-secure. So what exactly is going on here? How can we get some kind of key exchange, a secure key exchange, between our endpoints if we don't have a secure channel between them to begin with? Well, the example I'm going to show you actually uses colors. We're not going to get into the actual calculation of how Diffie-Hellman does this because it is way, way beyond the scope of this exam, and we have to stop somewhere. So if you're studying for your NP security eventually, which I think is a great idea, your IE security, or you're just curious, there are plenty of online calculators that will show you the several values that would be selected, and then you get into this modulus and a calculation and an exchange. That's way beyond what we need to do right now, but I just want you to get an idea of how Diffie-Hellman works. And what I'm going to do here is use an illustrated example from Wikipedia. It's in the public domain, and I'm glad of that because frankly it's the best example of how Diffie-Hellman works that I've ever seen without getting into moduluses and 16 calculations and that kind of thing, because we have other things we got to cover with our time. So having said all that, here's what happens in Diffie-Hellman using colors instead of numbers. First off, your two endpoints, which when named will always be Alice and Bob, it seems, they will agree on a starting color. Now, this color does not have to be private. So this can actually be negotiated before your secure channel comes up. So they don't care about this particular value being private. In this example, they choose yellow. What happens then is that each party independently selects their own separate secret color. And here Alice has chosen a form of red and Bob has chosen aqua. What happens is, step 3, each party mixes their color with the mutually agreed upon color. And then that's what they actually exchange. Now, after that exchange of colors, each party mixes its private color with the mix it received from the other party. And if all is well and nothing got changed with any values along the wire, over the wire, the resulting color will always be the same on each end. So if we use numbers here, you could see what would happen. Now, each party would agree on a starting number, and it would not have to be private. Then they would each select their own private number and run an algorithm against those two values. And then the result of that algorithm is what is actually exchanged. So what's really happening here, in my humble opinion, is that they're kind of working together on a secret key. We're not having the classic pre-shared key exchange where Alice sends Bob her key, Bob sends Alice his key. They're kind of working together, really. But the key is, no pun intended, that they do agree on a starting value to begin with. That value doesn't have to be private, so that can go over in the non-secure channel, and then the only other thing that's really exchanged is this mixed color, or using our numbers, it's the result of the algorithm, and if the secret numbers aren't known to the hacker, they can't do anything with it. So that's how Diffie-Hellman works in a nutshell, and I want to spend just a minute here with something called HMAC, because we saw this a couple of times during our transform set config, and I've highlighted one there for you, but you see HMAC there, you see it with 4 more ESP choices there at the bottom. Just wanted to give you a little information on what's going on there and what HMAC is, and it's literally one screen. I got a little bit on the next one for you. HMAC is the Keyed Hash Message Authentication Code, and it can verify the authentication and integrity of data simultaneously. What happens with HMAC, it's using a secret key and the hashed message, because what happens, the sending host is going to transmit both the hashed and unhashed versions of the data. And the recipient is using the secret key basically to run the hash again, and it hashes the unhashed data, which gives the recipient 2 hashed messages, the one that came in originally and the one it arrived at locally. And if they match, everything's fine. If they didn't match, then something's amiss and perhaps the integrity is not as integritous as we would like it to be. But when they match, then all is well. One thing you should know about HMAC, making those choices with the transform sets, is that HMAC performs absolutely no encryption. So just a little information there for you for Diffie, Hellman, and HMAC. And what we're going to do now is head over to a GUI. We're going to do some more VPN builds. We're going to do a little bit of walkthrough, but we're going to do it here on a Cisco GUI. And if you haven't seen one of these before, don't worry about it. It's very intuitive. You're going to enjoy it. But GUIs are definitely not going to put network admins out of work. I see that worry online a lot. As you're going to see, you still got to know what you're doing. It will always require someone at the console who knows what they're doing. And with that introduction, those GUIs are coming up next.